look at point C here. This is an interesting point. This point, it does have external loading like 3K here, and it's not connected to any pain or external reaction right here, right? It's just alone. This pin is alone. There is no external loading, and you only have two members connected to that. And we saw that both F1 and F2 became 0. So this is the first class of zero force member. It's called two members. Two member, 2 bar, and the plane, and there are no external loading / reaction. Then both are 0.
This wouldn't be possible with actual gravity, right?
No, yeah. In fact, when you have gravity, you have external loading. You see that? But assumption in Truss analysis is the members are just so thin and light. So the gravity force is never an assumption. Yeah.
So do you only count compression on bars? Because wouldn't like F4 right there have like a pull on it if 3K is going down right there?
So the way we actually do here, when we draw free body diagram, right? This dash line. When we work on dash line, whatever I cut here, the assumption I put tension positive. So I put force going this way, and this way, and this way. And this gravity is coming 3K is given to us, so we just put it there. But if I want to cut the bars, the assumption is tension is positive. But if I get negative, that means just the force in the other way, which is compression. Right? So you make an assumption, because we actually don't know the actual sign of the force. So you can just always say this tension this way is always positive. Now when you solve it, you get a negative like this. This means it's not tension, it's compression the other side. If it's not tension, it's compression. Okay? So the best example of class 1, 2 members is just point C. No external load. I don't have a 3K or I don't have something like pin roller connection, anything. It's just free. 2 members connected to that, so you can immediately recognize it and say this is 0, this is 0. This is good before you actually start analyzing the structure. You can kind of clean it up. Before you actually solve it, you can just say, you know what? This is 0 force member. I can just clean it up. Now this is my structure. Now let's solve it. You see?
You're saying that's 0 because it's not attached to a fixed point, is that what you're saying? Or
because of this. Read this again one more time. Because 2 bars were pinned at a point and there were no external loading on it. So the force in both of them was 0. So if the force is 0, you can just eliminate them. Because the purpose of Truss analysis is to find the force in your members. So if you already know it's 0, just get rid of it, right? The second part, this is category 1. Category 2 is 3 members. 2 of them are collinear or aligned. And there are no external loading / reaction. So in this case, if I write it here, this is, let's say this is a pin member 1, member 2. Case 1. 2 members connected to pin, no external reaction at this pin. Then both of them are 0. Forcing these 2 members 0. This case, you have 3 members. But 2 members, so member 1, 2, 3, right? They are pinned together, no external reaction. 2 of them are collinear along line. They're aligned. So in this case, these 2 we don't know, but the third one is immediately 0. So how can you prove this mathematically? Let's say this is a problem. I have a joint, you can do that?
So
Yeah.
it would just be 3 is equal to 2 minus 1, right?
Well, let's put it this way. I have a pin and 3 members are connected to that, and 2 of them are aligned line. Then the force in the third member is 0. But I can't say anything about member 1 and 2. But the force in the third member is 0. How do you prove this mathematically? You have to start with this joint free body diagram and write the equation for joint. Let me do it. So this joint, right? Here. Let's say that's the joint, right? You have member 1, member 2, and member 3. These are 3 bars connected to that joint. And 2 of them are aligned, right? The third one, however, is not. It doesn't have the same alignment. So it has angle theta in these 2. Now I want to prove that F3 must always, in this case, must always be 0. How can I do that? Well, if I draw FED for that, there is a force coming, F2, member 2, there is a force coming from member 1, and there is a force coming from member 3. So you have F1, F2, F3. This simply, this joint, free body diagram for this joint, right? You have 3 forces here, right? So now, you see we choose the axis right, X, Y, like this, right? Now, I say, let's just rotate it a little bit and align it with this structure like this. You can do that, right? X, Y. You can choose your axis, wherever you want to put it, and their direction. You can, that's your choice. It's arbitrary, right? So in this system, now I ask you, write the equation of equilibrium. So I have summation of force in the x0. So you get F2 plus F3 cosine theta minus F1 is equal to 0, and summation of force in y0. These are the joint equation. So we have F3 sine theta F3 sine theta is equal to 0. So theta is not 0 because the third part has some direction with the first 2 parts. The first 2 parts they have the same direction, but the third part has some different direction, right? So theta is not 0. So this is not 0. So something multiplied by non-zero is 0. So what is this?
0.
This must be 0. Right? So F3 must be 0. So if you put F3 0 here, what can you say about F1 and F2? They're equal. But you can't say they're 0. You can't say anything about them. You can just say they're equal. Right? So these two cases, you use to kind of brush or clean up your structure before you start into the doing. Example,